You step under a pull-up bar and wipe your palms on your shorts. The metal feels cool and a little gritty as your fingers close around it. You lift your feet, settle your weight beneath your shoulders, and glance at the timer. The first few seconds feel controlled. Pressure builds where the bar crosses the base of your fingers. Your palms warm up, your forearms tighten, and the metal starts to feel smoother. Your little finger begins to uncurl before the others. You squeeze again, but it never quite returns to its starting position. Your shoes touch the floor and the timer stops. One clean number now stands in for everything that happened, where you placed your fingers, how your skin pressed against the bar, and how fatigue changed your grip as the seconds passed. We can place a Neanderthal hand beside yours, at least in skeletal form. Several bones look unusually robust. The bones beneath the fingertips are relatively broad, and the base of the thumb looks heavily built. The comparison with a modern athlete seems almost automatic. A large, solid-looking hand appears built for a large result. Now remove the skin pressing against the bar. Let the forearm muscles, tendons, nerves, and subtle changes in posture fade away. Leave only the bones. The fossil does not preserve the muscle mass, tendon properties, nerve activity technique, fatigue, motivation, or body proportions that shape the living performance. Researchers can study the framework and test which movements certain joints may have favored. They cannot directly measure how hard that individual could grip. At the base of the thumb, the trapezium meets the first metacarpal. Researchers who compared these joint surfaces in 3 dimensions found average differences between the Neanderthals and recent humans in their samples. They also found considerable variation within both groups. In much of the Neanderthal sample, the joint shape is consistent with the thumb held fairly straight and drawn toward the hands. The fingers wrap around an object crossing the palm while the thumb braces it from the side. This is called a transverse power squeeze grip. Experiments with living hands show that people can use this grip to control some hafted tools. The fossil anatomy suggests that certain thumb-braced positions may have handled loads effectively. It does not show how much force any individual produced during a particular task. Other parts of the hand offer evidence about repeated activity. The muscles and tendons are gone, but some of their attachment sites remain visible on the bones. These sites are called entheses. Researchers first examined skeletons from people with historically documented occupations. The comparison helped them interpret patterns in attachment sites linked with different kinds of long-term hand use. When they applied the same method to Neanderthal fossils, they read the patterns as evidence of frequent precision grasping. Entheses do not record one specific movement. Age, development, biology, and many activities over a lifetime can affect them. They offer clues about habitual use, while the thumb joints offer clues about mechanical position. Neither can measure the full performance of a living hand. Together, the findings suggest a hand suited to thumb-braced power grips and regular, precise finger movements. A short reconstruction can put both findings to work in an ordinary task. The scene is plausible, not recorded. A Neanderthal sits with a wooden shaft across the knees. One hand steadies the wood. The other holds a short handle fitted with a stone edge. The fingers close firmly around the handle, and the thumb braces it from the side. The edge moves along the grain. A pail shaving lifts from the wood curls and falls beside the knee. During the next stroke, the resistance changes. The wrist turns slightly. The fingers loosen, slide higher on the handle, and close again. After several passes, the tool stops. Fingertips move across the worked edge of the shaft and find a shallow ridge. The tool shifts, the angle changes, and another controlled shaving begins to form. The firm grip carries the tool through the stroke. The fingertips guide the adjustment afterward. Power and precision belong to the same task. The exact handle movements and purpose are reconstructed. Archaeological evidence shows that some tools from Neanderthal-associated Middle Paleolithic settings were hafted. Microscopic wear can show contact between a stone tool and a handle. Preserved residue on particular artifacts has also revealed adhesives such as bitumen. Each trace answers a different question. Polish and scraping near the base of a tool may match movement inside a handle. Chemical testing can identify residue that once adhered to the stone. Shape alone tells us less, because a stone edge that could be mounted was not necessarily used that way. Making a hafted tool required several physical steps. The handle had to be shaped to hold the stone. The cutting edge needed a workable position. Where adhesive or binding was used, it had to be prepared and applied. During use, the stone had to stay aligned. A damaged connection needed attention before the tool could work reliably again. The handle also changed how the object met the hand. Its thickness set the space between the fingers and palm. Its shape affected where pressure built during a stroke. It let the hand hold the stone edge against the material at the angle the task required. No surviving artifact shows the exact finger position of every person who used it. Wear and residue reveal what some tools could do and how some were assembled. The hand fossils and the artifacts offer related evidence, but they rarely come from the same known individual. Variation among Neanderthal fossils makes a single hand model hard to defend. Some thumb joints fall closer to the recent human range than others. Geography, development, sex, inherited anatomy, and habitual activity may all have shaped the differences between individuals. Different tools also place different demands on the hand. A hafted implement, a loose stone flake, and a surface being inspected do not require identical finger positions. One anatomical average cannot represent every task across different people and populations. Robust bones still have a strong visual pull. A broad joint surface or thick finger bone can look like a performance result instead of one part of an anatomical system. Place an Olympic athlete beside it, and the picture starts to resemble a competition, even though no shared test ever took place. The evidence does not establish that a Neanderthal could overpower a modern athlete. It supports narrower conclusions about joint shape, repeated hand use, and tool-related behavior. Any number for absolute grip strength would depend on assumptions about living tissue and testing conditions that fossils cannot preserve. Back under the pull-up bar, your hands close around the same cool metal. A trace of chalk coats your palms. You adjust the space between your hands, settle your thumbs, and lift your feet as the timer starts. Pressure builds across the fingers. The little finger begins to open, then the next. When your shoes reach the floor, your hands release and the timer stops. Pale chalk remains on the bar where your skin touched it. Remove the living hand from that moment again. The pressure, muscle action, fatigue, and small corrections disappear. The bones stay in the positions they held inside the hand. The timer can tell you how long you held on because it measured the living test. With only the bones left, there is no second reading.